In this video, we're going to talk about osmosis. Now, osmosis is the spontaneous migration of water through a semi-permeable membrane. Um, and so if we look at our diagram here, this very well-drawn diagram, I might add, um, what we have here is a beaker that has a solution in it. And in that solution, we have a semi-permeable membrane that is separating a concentrated solution, and the solute particles are being represented by these red dots and lines, and pure water on the other side. And so osmosis tells us that water is going to flow from an area of high concentration, that is low solute concentration, to an area of low concentration of water. And so what we'll actually see is a net movement in this direction as water molecules will flow through the semi-permeable membrane and into the more concentrated solute solution. Now, the question you might ask is, well, why don't the solute particles go the opposite direction? Well, that's where that semi-permeable membrane comes in. A semi-permeable membrane is one that has holes in it that are large enough to let water molecules through, but small enough, generally speaking, to keep other particles from transmitting through that membrane. And so the only thing that can go through it is water. And so from that standpoint, this side has a higher concentration of water. This side has a lower concentration of water. And so the water will flow to try to even out that concentration difference. That's what osmosis is all about. Now, if we take that idea of a semi-permeable membrane and put it into other kinds of contexts. So here we have the use of a U-tube where we've got, again, water, in this case saline solution on one side, seawater, which is considerably more concentrated on the other side. And what we will tend to see is that the saline solution will flow through the membrane into the seawater solution in an attempt to um, even out the concentration. And what we'll end up getting is at some point we will get a differential where the more concentrated solute solution will end up having more liquid in it overall than the less concentrated solution over here. We'll eventually hit a point where there's an equilibrium, a balance. Water molecules traveling from left to right even out those that are traveling right to left. Well, this difference is related to what we call osmotic pressure. If we were to take some kind of an object and push downward on this side of the tube to get them to go back to being even again, that amount of pressure that is applied is what we would call osmotic pressure. So we can use osmotic pressure to calculate just how much force would be required to even that out. So we can look at it as the official book definition is the pressure applied across that semi-permeable membrane to stop the flow of water from the area of high concentration to the area of low concentration. What we can see also here is that we have an equation that allows us to quantify that osmotic pressure, where the osmotic pressure is equal to the molar concentration times R, which is the universal gas constant. We'll talk about that more in a second, and T, the Kelvin temperature. Now, this particular equation is actually incomplete. As we have seen with other colligative properties, there is the Van Hoff factor to consider. And remember, the Van Hoff factor is associated with total ion concentration. So once again, we can estimate I by the number of ions produced per molecule. And so I is equal to 1 for non-electrolytes. I is greater than 1 for all electrolytes. And again, we can estimate it this way, but oftentimes we will be given the value for I, especially in more concentrated solutions. Now, as far as values of R are concerned, there are several that are possible. All of the values of R are completely dependent upon what unit of pressure we are going to use to describe the osmotic pressure. Notice that everything else in these equations, liters, moles, Kelvin, they're all the same. They're all the same in the same places. So the value that you use for R depends upon the value of pressure that you're going to use for osmotic pressure. So keep that in mind. If you're told that the osmotic pressure is, 25 atmospheres, you're going to use the value of R that has atmospheres in the unit structure. If you're told that the osmotic pressure is 30 torr, you're going to use this bottom one. Now notice also that the value for millimeters of mercury and torr is the same. That's because millimeters of mercury and torr are practically the same unit. In fact, the unit of torr is millimeters of mercury. It's named after Evangelista Torricelli, who invented the barometer. And that's where that comes from. Let's take a look at an example of a calculation that we can do out of these. So we are told the total concentration of solute particles in a fluid inside a red blood cell is 0.310 molar. What is the osmotic pressure of this fluid at body temperature? The membrane surrounding the cell is semi-permeable, which is true for all animal cells. So let's set this up. Pi, which we're just going to use the capital letter T here. Osmotic pressure is equal to I times M times R times T. Now, one note of clarification here. When we are told the total concentration of a solution, total concentration is equal to I times M. Total concentration includes the Van Hoff factor already. So we don't need to go searching for it. It's been included in this 0.310 molar. So in this particular case, that covers both of them. Now, in this example, in our calculation here, our osmotic pressure that we want is 0.310 molar times R. R, we can choose whatever value we want. I'm going to go with 0.0821 liter atmospheres per mole Kelvin. Temperature 37 degrees Celsius. Now before we go putting in that 37, take a look at my units here. I need temperature to come cancel. I've got Kelvin units here, Celsius units here. So I'm not going to put in Celsius, I need to convert this to Kelvin. Kelvin temperature, remember 273.15 plus 37. So if I put that in, 273.15 plus 37, I get 310.15. My value is only to the ones place, so I round to the ones place as well. 310 Kelvin is the answer there. So that's the temperature I'm going to put in there as well. And if I put it all together, 0.310 times 0.0821 times 310 would give me an osmotic pressure to 3 significant figures of 7.89 atmospheres. So it is really just kind of as simple as that. Now, where can we use this kind of information? Where is this actually relevant? Well, one application that we find for osmotic pressure is something that happens in our cells. We see osmotic pressure applied especially when we look at blood cells. If blood cells are kept in the appropriate environment, that would be what we call an isotonic solution. They tend to keep their normal dimpled shape. If we take our blood cells and we introduce them into a solution that is hypertonic, that is, has way too much solute dissolved on the outside. So, like if we were to put this cell in a concentrated saltwater solution, what would happen is water would start to flow out of the cell, and the cell would shrivel up like this and go into an extreme survivalist mode, or just eventually wither up and die. On the flip side, if I take that cell, which is in this isotonic solution, and note, the isotonic solution does have some stuff dissolved in it on the outside. It is not pure water. If I take that and I put it into pure water, now the water on the outside recognizes that the concentration inside the cell is too concentrated. Water starts to flow into the cells, and the cell starts to swell up and get really, really big, and eventually could rupture and burst. Another process that we see is in desalination. In desalination, what we see is a process that involves most removing ions from seawater. So in particular, in countries that are near oceans and do not have freshwater sources, desalination is really one of the life-saving processes that allows them to have water on a regular basis. Now, the process of desalination can occur one of two ways. You can distill the stuff, which involves a pretty significant investment of energy to get all of that seawater to boil and then collect the purified water at the end. The other issue with it is that distillation creates water that usually doesn't taste very good, and they have to add some salt molecules into it to help give it a little bit of taste. The other process is something called reverse osmosis. Reverse osmosis is where we force the water through a series of pumps into these semi-permeable membranes. And so under high pressure, we actually take the osmosis process and we reverse it, force the high concentration water into a more purified state, and then pump the pure water out at the end. And this is how a lot of bottled water is made as well. So just a couple of interesting kinds of purposes. In our next video, we will look at another application of osmotic pressure and talk about something called Henry's Law.